Hi everyone. For a substance, there are typically three phases: solid, liquid, and gas. Thus, there are actually 6 possible phase changes or transitions. We will see those in a bit. Also, there are enthalpy changes associated with these transitions, and we'll focus on the enthalpy of vaporization and the enthalpy of fusion. We should have time to do a couple of practice problems as well. Let us set up the 3 phases that we are going to be looking at. Let's keep it simple and let's just think of water for now. And you know that water can be a solid, a liquid, or gas for the most part. There is supercritical liquid, but let's not discuss that. Maybe that's for another video. And we have process A and process B as this water is going through those phase changes. What do we know about A and B? A and B, they are both endothermic. We need to add heat to go from solid to liquid and liquid to gas. Endothermic. And we know that endothermic means that your delta H is positive. Okay, let's take a look at now these 6 phase changes. And the first one, we'll do solid to liquid. Give yourself some space above the line, or above where we're going to write solid. Don't draw an arrow yet, to liquid. Okay, I'm going to draw a curved arrow on the top, like this. Alright, we all know that has a name. That's melting. And there is a delta H associated with it. That is the delta H of what's called fusion. Now, that's enthalpy, but because enthalpy is equal to heat, the Q term, we could call this the heat of fusion. Let me write that somewhere. The heat of fusion. And yes, we'll see the heat of vaporization in a second or two. Is there anything else I want to say about this? No. What about for liquid to gas? Liquid to gas. Another curved arrow. That is evaporation. And that has a delta H associated with it, a change in enthalpy, delta H vape. And again, I'll just write it here. You'll mostly hear this as the heat of vaporization. Of vaporization. But we also have the backsword process for each of those 2 phase changes. If you go from liquid to solid, what is that called? That's freezing. And the magnitude of the enthalpy change is identical to this, right? It's the same reaction or same process except backwards, but you're going to use the opposite sign. See, what's going to be happening is that we're going to calculate the heat, the Q term, using these enthalpy terms. This one here, gas to liquid, what is that called? Oh, condensation. Right, when you see like dew on grass in the morning, the humidity, the water in the air is condensing on the grass. Condensation. And yes, its enthalpy change is the same number, except you're going to take the negative. Because going in the direction from gas to liquid, that is exothermic, right? The system is losing heat as it condenses, or the liquid is losing heat as it solidifies. I said 6, right? 6 phase transitions, or 6 phase changes. Where are the other 2? Solid, directly to gas. Okay. You've seen these with, mothballs? You have solid mothballs, and then all of a sudden they're gone. They seem to evaporate, and also dry ice. Solid carbon dioxide goes to gas, bypassing the liquid phase. Bypassing the liquid phase, that is sublimation. It sublimes. And yes, there's a delta H sub. Let me challenge you with this now. What is that process called? When you go from a gas, molecules in the air, that all of a sudden become solid? That is called, what is that called? Deposition. Deposition. From the word deposit. And yes, negative delta H sub. So keep these in mind, the signs, and what is associated with melting and freezing. It's the fusion. What's associated with evaporation and condensation? The vaporization, the delta H vaporization. This is interesting, this deposition. I have a friend who works at Gillette, the razor blade company, and she does vapor deposition. Vapor deposition of what? Of titanium. Titanium? Gaseous titanium deposited onto steel blades. Onto steel blades. You know, for the razors. We're going to need our values for water. So let me give you those. The delta H of fusion for water equals 6.01. Now, take a look at the units. Kilojoules per mole. There's no temperature term there. Okay. Not only that, you're only supposed to use this number during the phase transition. And this is associated with melting and freezing. So for water, that's at 0 degrees. You're going to use at only 0.0 degrees Celsius. And that's it. We're going to have practice. Don't worry. Heat of vaporization is 40.79 kilojoules per mole. And then this one is only associated with evaporation and condensation at the boiling point. So we're going to use at 100 degrees. See, so I should have said that. These numbers are the freezing point and the boiling point. You do realize that the freezing point is the same as the melting point. The boiling point is the same as the condensation point. The equations that you're going to be using that use these two values, these two constants, look like this. Q equals N. N is for mole, okay? I think we're used to seeing mass there, grams for instance. Delta H fusion. And again, this is at the freezing point. Doesn't necessarily have to be water. We could take any substance, and for looking at its transition from solid to liquid or liquid to solid, we're going to use this equation. But that transition has to be at their freezing point. This is analogous to vaporization. It will have to take place at its boiling point. Put these in boxes. That's for your equation sheet. Boiling point. Okay. So you notice that there's no delta T term. I think what everyone was expecting was a Q equals mCs delta T, right, with a specific heat capacity. We're actually going to need that for at least one of these problems we're going to see, the specific heat capacity. And we're going to use the reagent CS, remember that? H2O, and we're going to specify liquid. That number is, we're going to use 4.184 in our calculations in this video. Joules, not kilojoules. So there's a discrepancy there. We have to match them if we're going to use both of these equations or both of these constants. Dot, and there is a degree Celsius there. Or it could be degree Kelvin. It doesn't matter because, as you recall, your equation is delta T. So it doesn't matter if you had Celsius or Kelvin. Remember this equation? Because we're going to need that if we're changing temperatures of the liquid water. So for this one, we're going to use, specifically for this number, right? We're going to use when liquid water changes temperature. Liquid water changes temp. Okay. Again, no delta T here because we're only going to use it at 0 degrees Celsius or 100 degrees Celsius, the freezing point and the boiling point of water. All right. These are the cues associated with phase transitions. So let me put that. These are the heats. See, this is not a phase transition. When you're changing just temperature within the liquid phase, it's all liquid. But here you are changing the phases. These are the heats associated with phase changes. These up here, right? These 6 arrows. Okay. Now, I never gave you the definition of delta H of fusion, delta H of vaporization, but I think you could figure it out from the units. Okay. This is the amount of heat required to melt 1 mole of solid. Oops, losing ink. 1 mole of solid where? At the freezing point. Freezing point. Oops. Uh-oh. Not vaporization. Heat of fusion. Heat of fusion. Heat of fusion, solid. Okay, solid to liquid. See how easy it is to get turned around, so you really got to be careful. I have to be really careful. When I took this exam in college, yeah, this is what I had problems with switching up terms. The heat of vaporization is the amount of heat required to evaporate, or call it vaporize. Vaporize what? 1 mole of liquid. But again, it's at the boiling point, at a specific temperature. Okay. So I'm going to do one problem with you, and then for second problem, I'll show you how I did it. I pre-did it already. The first problem, if you feel like you understand this, right, and you do have your cheat sheet, okay, your cheat sheet and your numbers, why don't you give this a shot before you see how I solve for it? Okay. Calculate the amount of heat in kilojoules deposited on the skin of a person burned by 1 gram of liquid water at 100 degrees Celsius. Okay, so that's nasty. A gram of 100 degree water, liquid, is going to transfer heat to your skin. We're going to compare that amount with the amount as if they were burned with 1 gram of steam. So we have liquid here and we have steam here. Is that going to make a difference? Yes. The steam has to phase transition into a liquid and then it has to reach body temperature. Because in both cases, you're assuming that 100 degrees Celsius water, whether it's liquid or steam, will cool to 37 degrees, thus giving off heat. Why don't you pause the video and give this a shot? Okay, how would I do this? I gotta be very careful because I have a tendency to get things turned around. So I'm gonna map it out. 100 grams of water, liquid. I'm doing the first part. Calculate if the 1 gram of water, let's say 1 gram of water at 100 degrees Celsius, liquid, going to H2O, it's still liquid, okay, 37 degrees Celsius. So we have one process, A. This is not a phase transition. I don't think. It's not. It's not a phase transition. This is a normal MCS delta T problem. Did you have that on your paper already? Q equals MCS delta T. So the Q associated with this process, it's not a phase transition, is 1.00. We need this heat capacity, specific heat capacity, 4.184. Okay, so I am using my notes, 4.184 delta T. So this is interesting. Delta T is always final minus initial. Final is lower, 37.0 minus 100. What that means is that this term is going to be negative. Well, that makes sense. A negative Q, this is losing heat. It's giving away heat to the body. So this is exothermic. We expect the delta H of this to be negative. We expect the Q to be negative. Okay. When you do those calculations, negative 263.6 joules, and we're going to convert that to kilojoules. Negative 0.263, should have rounded, 6 kilojoules. And just to show that the grader that you know what this means, you could say, well, that's giving off heat when it's negative. So the water is giving off 0.26, around now, kilojoules of heat deposited onto the skin. Okay? But the process is a negative Q. The amount of heat given off is positive. Okay. Now, what if they started with steam? You have 1.00 grams of H2O gas, G for gas, at 100 degrees C. So that's a different starting point than the first example. We have to phase transition into the liquid form before we start cooling the liquid from 100 to 37. So this is a different process. We're going from H2O gas to H2O liquid, but it's still at 100 degrees C. Help. I need better pens. 100 degrees C. And then I'm going to try one more time the purple. And oh, there we go. And then we have to cool that water. It's going to still be H2O liquid, now at 37.0 degrees C. But that process, this is A, this process B is the same as this up here, right? It's the same process. So we're going to use this number again. We're going to add it. But we need to figure out this one. You notice that it stays at 100 degrees. This is a phase transition. So now for process A, okay, we can label this also. This is process A for this problem. But here, process A is what? Q equals N delta H. So gas and liquid. Gas, liquid, that has to deal with the delta H of vaporization. Delta H of vape. Okay, and let's just rationalize this. This is losing heat. It is exothermic. It's going from gas to liquid. We're actually using the negative of the delta H vape. So I'm going to put the negative sign and I'm going to squeeze it in here. Okay, maybe put parentheses. That N is a moles. I forgot about that. This is moles. So we're going to convert 1 gram of water times what? 1 mole. The molar mass is 18.02 grams equals 0.0555 moles. So that's the number we're going to use up here. 0.0555. The delta H vape of water at 100 degrees Celsius is 40.79. But since we're going in this direction, from gas to liquid, we're using the negative. That makes sense. It's exothermic. 40.79. And this is already in kilojoules per mole. So normally I don't put the units if I'm very confident that I know the units of the terms. And what do I have here? I calculated this already. Negative 2.26 kilojoules. Okay. So the total amount of heat given off is A plus B. So A in this case is negative 2.26 kJ kilojoules. Part B I said was the same as this part A, or process B is the same as this process A in the first calculations. So we are adding, it has to be the Q, it has to be this number here, right? Another exothermic term, negative 0.264. And I get here negative 2.52 kilojoules. And what that number means is that 2.52 kilojoules of heat was deposited on the skin. I'm off screen. Deposited on skin. And we could compare it to the original. So take a look at that. So by making the steam has to first phase transition into water. That gives off heat. It gives off actually a lot of heat. 2.26 kilojoules. And then it gives off more heat to lower the temperature of that water from 100 to 37. So just keep your processes straight, draw them out, and yeah, you may have to calculate several Qs. We have a Q here, and then the Q that was used for this B was Q equals MCS delta T. Okay. One more problem, shorter. Why don't you try this without my help first, and then come back to the video when you have something on your paper. Alright, the way I did this was, again, I'm trying to be very, specific or very explicit about my processes. And also, I put a little note to myself, in this case, it's endothermic. We're going from solid to liquid. We need to add heat to melt it. To melt, this is delta H of fusion right there. And we're using the positive number, not the negative. Okay. So we're going to calculate an A and we're going to calculate a B. The A is using the heat of fusion. I have the moles already. Oh no. Is that the right moles? Oh man. Give me 1 second. I think the number is correct, the calculation is correct, but the moles is not. Oh, you know what? I freaked myself out. It's 100 grams. It's 100 grams. It's not 1 gram. So that's why the moles are different. Okay. And anyway, I have the first process. It absorbed 33.4 kilojoules of heat. In the second process, we're using Q equals MCS delta T. It absorbs. So this is the amount of heat required, right, to first melt and then warm it to body temperature. See, this term is now positive because the final temperature was 37, but then initial was 0. Okay. You add those two numbers up and you get the amount of heat required for these two processes added up.